All right. Hi, I'm Nick Zafelli, and I'm a senior.
My name's Steven Petrowski, and I'm also a senior.
I'm Timothy Flisk. I'm a senior.
I'm Jeffrey Liu. I'm also a senior.
I'm Taylor Malind, and I'm a senior.
All right. So, hello. We are York Community High School, and this is our solution to this year's M3 challenge. So, as homelessness and housing shortages remain consistent issues in our society, being able to accurately predict how these phenomena will continue to change in the future is very important if we hope to make progress towards solving these problems. So to start, we had to make a couple of global assumptions. The first being that historical homelessness and housing data are going to be predictive of future trends. Assuming this is important because it allows us to assume that the things that caused homelessness and housing shortages in the past will continue to cause them in the future. Secondly, we assume that homelessness and housing are directly related to the economy. This allowed us to use economic wisdom to create and justify our models. And thirdly, we assume that the housing market won't reach some sort of theoretical limit during our time period. And this just allowed us to ignore any issues with growth towards a limit, which would make our models unnecessarily complex. So question one, our task was to predict changes in the housing supply in Seattle and Albuquerque over the next 50 years. So we also had to make some local assumptions for this question. The first, kind of reiterating what I just stated, is that usable space is not a significant constraint. And secondly, we had to assume that average longevity of housing will remain unchanged. And we did this so that we could assume that people will continue to move houses at the same rate as they do currently. So our approach for this question was to create a midline sinusoidal regression. And we came up with this idea based on the economic theory of the business cycle, which has two main features. The first being an overall linear increase. The economy generally trends up in the long run. And secondly, periodic deviations such as recessions and periods of growth. And a midline sinusoidal regression is optimal to model this question because it is not complex and it fits the data very well considering housing is related to the economy.
Thank you, Nick. So on the right, we can see the more formalized version of what he was talking about earlier. We have our linear term, which is governed by parameters m and beta. We then add our sinusoidal term, which is transformed by parameters alpha, omega, and phi. Combining this function, we can create any shape of midline sinusoidal model to fit our data. Optimizing our parameters above, we arrive at these values for Albuquerque and Seattle. With these graphs, we can visually confirm that our model closely follows the data and is consistent with the economic theory of the business cycle. Over the next 50 years, we predict a 35% increase in total housing units in Albuquerque and an even greater increase in Seattle at 98%. Comparing our model's predictions for 2022 to the actual data of 2022, we were off only 0.15% for Albuquerque and 0.54% for Seattle. We are confident in our predictions as our R-squared value for both of our models are above 0.99. Our model had some strengths, the first of which being that it was periodic, which leads to accurate predictions in the short run. And secondly, our residual plot was mostly homoscedastic, meaning that it had minimal discernible patterns. This is a strength, as when a residual plot has a clear pattern, unlike ours, this implies that there's a better model to fit the data. That being said, though, we did have some weaknesses. Firstly, we did fail to take into account land restrictions, which could impact our long-run predictions. And secondly, the period of our models is close to or even shorter than the time frame of the data given. This means our models could be sensitive to some noise or just randomness within the data. However, this is an easy fix as we can simply collect more data, or more specifically, over multiple periods.
For question 2, we were tasked with predicting changes in homeless population in Seattle and Albuquerque over the next 50 years. We made 4 local assumptions for our problem. Our first being that population, income, and median housing price are all well approximated by linear regressions. Our second being that income follows a normal distribution, with its mean being the median yearly income. For our third local assumption, we had to define a certain income cutoff for homelessness. We defined this to be the median housing price divided by 30, and we arrived at this conclusion based on the reasonable assumption that if an individual cannot afford a 30-year mortgage for a median-priced home with their entire income at the cheapest possible financing rate, then they are most likely not able to afford housing. For our fourth assumption, we assumed that we were able to dismiss 2021 data points for homeless population due to a lack of point of contact counting for homeless population, unhoused population. We had 6 variables: time since 2010, our median income, our median housing price, our standard deviation of our normal curve, our total population, and our total homeless population. For a general overview of our model, we essentially constructed a normal curve of income for a given year defined by its mean and standard deviation. Our mean was our median income as we previously defined, and our standard deviation was computed from our previous data and linearly extrapolated through time. Once we had our normal curve, we could find a certain proportion of the population under a given income bracket by integrating under the curve up to a certain limit. This is where our homeless income cutoff comes in. By integrating up to that limit of our normal curve, we can find the proportion of the population which is going to be homeless defined by our income bracket. And once we have that, we can multiply that by the total population, which we previously found, to find our total homeless population. For the computation of standard deviation, we essentially worked backwards from our already given data. Because we had homeless population and total population for multiple years, we could find the proportion of population which was homeless, and then we could find an upper bound which we would integrate up to find our standard deviation, to essentially construct a normal curve for a given year with a certain standard deviation. Once we had our data points for our standard deviation for each year, we saw that it was approximately linear, and we could construct a simple regression which would model it well.
Thank you, Tim. So to look at a general overview of the way that our model works, we start with 3 sets of time series data. First, the population, second, the average income, and third, the housing price. And as Tim described earlier, we can take these 3 sets of data and create a 4th set, our estimated standard deviation, using the formula shown previously. Now, with our 4 sets of data, 3 given and 1 derived, we can convert all the economic data through inflation as needed and perform, as stated before, linear regressions for each of these. Now, you can see that some of these data points may not look as though they follow a linear regression. However, we know from economic theory and our general societal understanding that the overall trend is indeed linear. But we can see that because our data is of a small sample size and there is always noise in real-world data, it may not look to be best linear here. So as we make these regressions, we can substitute them into our formula for the distribution model, and multiplying by the population with our proportion that we estimate to be homeless, we can get our predictions for the number of homeless people. Now, if we look at our results, we see that we predict that Albuquerque has an increase of about 96% of homeless people over the next 50 years, and Seattle has an even greater increase at 132%. And if you look at the error, it's extremely low. For Albuquerque, we only had a percent error of about 2.04%, and for Seattle, 3.54%. And if you look at the residual plot, especially towards the end, again, it's mostly homoscedastic. While there is a little bit of periodicity here, it remains very close to the line of 0, indicating that our model generally has the appropriate level of complexity for this problem. So our approach had a few strengths. Firstly, that it draws from multiple sources of data, meaning that if we were to try to predict in the future with data that we don't have right now and we collect later, even a little bit of noise wouldn't have an extremely large impact in the accuracy of our prediction. And second, we see that from our past data, the R-squared values are extremely high for almost all of the regressions, meaning that even though, as noted before, it may not look to be strictly linear, the linear approximation works very well. However, this wasn't true for every single one of the time series data points. Some of them did not have the best R-squared values, but again, this is because of the noise in real-world data. We also assumed previously that income is normally distributed, but it's actually known to be log normally distributed. We decided to instead use the normal distribution because firstly, it's a good approximation in this specific case for the log normal, and using a more complex log normal, it would be adding additional complexity to the model that would lead us to overfitting instead of actually understanding the general trends in our data. Finally, because of our specific approach with the normal distribution, all of our regressions needed to have the same asymptotic growth rate. However, because we know from our understandings of the economy and overall societal movement, all of our regressions were linear and they did satisfy this requirement.
Question 3 asked us to find a plan to help a city address homelessness. Thank you. For our first local assumption, we assumed that a decrease in transitional housing caused an increase in homelessness. We assumed this causation from the correlation we saw in the data. For our next assumption, we assumed that 90% of the homeless population would opt for transitional housing. We got this assumption from a Denver sample that was done by the Denver Social Impact Bond. Finally, we assumed that the number of sheltered homeless people will remain constant at current capacity. And we assumed this because we saw no discernible growth in the data. That leads us to our solution, which was to build more transitional housing. Transitional housing is temporary residence for unhoused individuals. A resident of transitional housing will stay at this transitional housing project while they find stable housing and employment, and then they may move out after a few months. We chose transitional housing because it is a long-term and inexpensive solution. Transitional housing is also correlated with, inversely correlated with homelessness. As you can see here, Seattle, which had a 10-year plan that included funding transitional housing, had homelessness only slightly increased when transitional housing remained about constant. However, when the plan ended around 2015 and they cut budgets leading to a decrease in transitional housing, we immediately saw homelessness start to skyrocket. This leads us into our variables, the most important ones of which are our cost of construction variable, our maintenance cost per year variable, and our unsheltered homeless people variable. This variable comes from the total homeless population we found in question 2, subtracted by our constant of sheltered homeless people, which is about 6,000. For our construction cost model, with 90% of the homeless population opting to enter transitional housing and 150 square feet per unit for transitional housing, we found that the cost of construction will be about $264 per square feet. And we found this from the 2020 Washington State Legislature report. That led us to that model right there, which indexes cost of construction according to time. Thus, for our results, we found that over 50 years, it would take about $900 million to build enough transitional housing for all unhoused people. For our maintenance cost model, we found that about $1.6 per square foot per year was the cost of maintenance. And we found this from a engineering consult survivor forum. That leads us to our maintenance costs, which are about $5 million for 50 years. Our solution is adaptable to unforeseen circumstances such as economic recessions or severe weather, because since most of the cost is upfront, the maintenance costs are very low, and it can handle the severe weather conditions. However, it's not adaptable to migration because it might not be able to handle the sudden influx of homeless people, and it is not adaptable to natural disasters because it might not be able to handle the conditions. Our strength is that it recognizes Seattle's previous shortcomings, creates employment for Seattle's residents, and it's inexpensive and reusable, especially given Seattle's budget of about $7.1 billion, which is increasing. However, our areas of improvement is it fails to address issues with drug addiction and mental illness, which are contributing factors in the cycle of homelessness, and it fails to offer help to every homeless person. In conclusion, we found that Seattle and Albuquerque will have an increase in housing over the next 50 years. Both cities will have an increase in the homeless population, with Seattle having a drastic increase, and transitional housing is an inexpensive and effective way. Thank you for your time. We would like to provide thanks to SEAM for hosting this competition, the judges for listening to our presentation, and our coaches for supporting us along the way.
Great, thanks everyone. So we can take some questions from the judging panel.
Hello, everyone. Can you hear me okay? All right. So I have a question. It's not even about the mathematics and the models. I'm curious as to how the COVID-19 pandemic showed up in your historical data. Because you had a lot of data the past, 10, 15 years. And did you see anything that indicated that there was a pandemic? And did you think about the effect on the pandemic and all these things on homelessness?
So when we did start our initial visual exploration of the data, we did obviously see that there was a major shift in the trend, right? So for example, in the recorded number of homeless people, we saw that it was generally increasing. And then suddenly there was, I think it was in 2021, we had a sudden dip. And that led us to go research where there might have been errors in data measurement, which we did find, and that was part of our justification for throwing away one of the data points, which was very inaccurately measured. So that was one of the impacts. Second was, again, the economic impact, right? That cannot be ignored. But we do think that generally the economy continues moving in about the same direction. We saw across major economic events such as like the 2008 recession, it still generally follows the same trend. So we used as much data as we could, given we only have a very small amount, including the pandemic data to model our things.
Thank you.
Yep. Can you hear me too? Okay, good. In your first problem, in the first part, your linear trend is, you added sinusoidal trend. And you do show very high R-squared, so the model is good. If you remove the sinusoidal correction, is the model any worse? Did you look at any numbers that say, okay, that addition is really making a difference?
Wait, is this, yeah, okay. So without the sinusoidal term, it still models the general trend of the data very well. As we know that in the long run, as we stated in our presentation, the economy does tend to increase linearly. However, in the short run, which we would consider like, especially the 10 and 20-year data points, relatively short run, we know that housing can be very sensitive to economic recessions and growth periods. So we saw, first off in the data, we noticed that trend. And when we were doing our research, we noticed that sinusoidal methods are often used to model the economy. So the model wouldn't necessarily be bad without the sinusoidal term. It just makes it much better. And we thought it was a worthwhile inclusion that while it added some complexity and maybe some extra sensitivity to noise, it was still worthwhile.
Okay, thank you.
Thanks. I'll ask probably one final question, which was, I was also interested in your part one model. Correct me if I'm wrong, but I believe it didn't come into your part two model, which I wanted to ask about. So, like you're predicting where housing goes over time. You'd think this might have some impact on the homeless population. So can you talk about that decision? Was part one integrated in part two? If not, why not? And maybe given more time, would you do anything different?
One thing about homelessness is that it takes into account your income, which we weren't entirely sure would actually fit that same like sinusoidal regression. This is one thing I'd like to add.
We definitely were mainly looking at homelessness as an issue, like Steve said, of housing price. I think that our Model 2 definitely brings in a lot of data, but housing availability was not exactly one of those that we thought should be our main focus for homelessness.
You could see in the data from the 10 to 15 years that despite both homelessness and housing increasing, they didn't really seem to have much of an impact on each other. Mostly, homelessness seems to be caused by a inflated housing price market in which people simply cannot afford houses even though there are vacant houses existing for them.
Okay, great. I think we'll wrap you guys up there, but thanks for the presentation.
Thank you so much.
Thank you.